Now, after understanding and studying the preparation, the purification of colloidals, let us now understand the properties of colloidal solutions, which are very typical, very specific to this system. The first property which they show is called colligative property. Yes, it is the same which we have done in the chapter solutions. The property which depends on the amount of the solute in the solution and not on their nature. So these colloidal particles, yes, exactly, they show all colligative properties, your elevation, boiling point, depression, freezing point, osmotic pressure, and RLVP. But the only problem is this: since their masses are very, very large, very high, they are macromolecules, their masses are very large, the magnitude of these colligative properties is very, very small, and that is why it is of almost of no significance. So remember, they show colligative properties, but that of not of any significance. The reason is their masses are very, very high because they already are macromolecules. Tyndall effect. It is a very exclusive property which is shown by the colloidal systems. Now the property is, when a beam of a light is passed through the colloidal solutions, its path gets illuminated. Now this phenomenon is called Tyndall effect, and this happens because of the scattering of light by the colloidal particles, because they are already very large enough. This is not shown by true solution system or neither by the suspensions. Now what happens is, if this is your source of light, if we converge it by using a lens and passes it through a colloidal solution, this is our colloidal solution is, what we find is the cone which is formed by this converged light, which is called Tyndall cone. If we are observing it from the side of the direction of the light, we won't be able to see anything. It will be appearing as a translucent one. But if we are observing it at a right angle to the direction of the light, what we find is that the scattering of light is done by these colloidal particles. And that is how their path gets illuminated, and this is how we can see their path. So this phenomenon is called Tyndall effect. It was first studied by Faraday, but later on explained by Tyndall. That's why it's called Tyndall effect. Now remember, colloidals shows Tyndall effect only under two conditions. First, the wavelength of the light used and the size of the colloidal particle must be comparable. That is how their scattering takes place to the maximum extent. Second, the dispersion phase and dispersion medium must differ greatly in their magnitude of the refractive index. Then only the scattering of the light is visible. So the refractive index of the dispersion phase and dispersion medium should not be comparable. They should differ in their magnitude. Then only this becomes visible. This is what we have, Tyndall effect. The third property shown by the colloidal solutions is color. Yes, they show colors of very different type, and their color mainly depends on basically the three factors: the wavelength of light used. So that depends on the light which we are using to see them. The second is the particle size. The best example is gold sol, whose color changes from your purple to blue to golden as the size of the colloidal particles is increased, or the gold particle is increased. So when the gold particles are very, very small, very fine, the color is purple. But further increased, it becomes blue. Further increased, it becomes very large, they are golden in color. So the color also depends on the size of the colloidal particles. And the third is the way the colloidal is observed. Like a colloidal solution of a milk and water appears blue to us in the reflected rays light, whereas the same appears red in the transmitted light. So how we are seeing, how we are observing the colloidal system, that again decides the color. But remember, color is a very important property of the colloidal system. The fourth property of the colloidal solutions is Brownian movement. The zigzag movement shown by the colloidal particles is called Brownian movement. It was first studied by Robert Brown, and that is how on the name of it becomes the Brownian movement. So this zigzag movement of the colloidal particles is due to their continuous collision with the other colloidal and the dispersion medium particles. Now this Brownian movement is independent of the nature of the colloidal, but it depends upon the size of the colloidal and the viscosity of the medium used. Smaller is the size, lesser is the viscosity, more faster is the Brownian movement. And this zigzag movement, you might have seen in the dark rooms when the sun rays comes, you can see the dust particles which I'm showing zigzag movement, that's called Brownian movement. It is there because of their continuous collision with the gas molecules. Now those dust particles, they are basically our colloidal system. So that is how what we have the Brownian movement. The fifth property is the charge on colloidal particles. Remember, always colloidal particles are charged particles. They are always having certain type of a charge on their surfaces. But remember, all particles of the colloidal, all colloidal particles of a particular colloidal system are having the same type of a charge. And that is why they never settles down, they're never able to come closer to each other because they repel each other. Like we know, like arsenic sulfide Sol is regarded as a negative Sol. We know starch Sol is a negative Sol. We know ferric hydroxide Sol as the positive Sol. So like these colloidal particles have one or the other type of a charge on their surface. Now how these charges comes again depends. We are not very clear about it, but yes, we know one of the two basic reasons. Some people say it is mainly because of their continuous Brownian movement, and as a result of their collision they develop some frictional forces due to which they develop charges. But other two basic phenomena which are actually more believed and they're more common are one is that they absorb electrons during the electron dispersion processes or during the preparation processes, or it is due to, which is main reason, is preferential. It is due to mainly preferential adsorption. Preferential adsorption. They absorb particular type of ion on the surface, and that is how they develop charges on the surface. Now this can be explained by taking an example. Like if silver nitrate solution is added to Ki solution, we know we will be getting AgI precipitates, but this AgI is in Ki solution. So what happens is, the AgI precipitates which you get, since the medium is having K plus and I minus, preferential adsorption of the common ion, remember, preferential adsorption of the common ion takes place. Now what is common between these two is the iodide ion. So iodide ion gets adsorbed on it. It's like this. So once these iodide ions gets adsorbed on these colloidal particles, these precipitates separates out on the colloidal range, they become negatively charged Sol, or they form directly the negatively charged Sol. So when the silver nitrate solution is added to Ki solution, we get a Sol of AgI which is negative Sol. Whereas, let me explain it to you like this. If the same thing is allowed to done in the reverse way, like Ki solution is added to silver nitrate solution, what we get is, of course, is AgI, but it is there in silver nitrate solution. Now in this case of AgI, the solution is of silver nitrate, Ag plus and N minus. What is common between the two is Ag plus. So what happens is, this Ag plus gets adsorbed on its surface like this. As a result, again we get a silver iodide Sol, but this is now a positive Sol. This is what is preferential adsorption is. So what we find is, these colloidals have affinity for a particular type of ion and they adsorb them on their surface, which is called preferential adsorption. Now as a result of this preferential adsorption, what happens is, these colloidal particles, they have what? Let us take the same example. Preferentially adsorbed ions all around their surface. And they form a layer around it. Now this layer is called fixed layer. This first layer is called fixed layer. Now outside this, since it is positively charged now, what will happen is nitrate ions will come and they will surround this whole system. Now this layer, second layer of nitrate ion or of the oppositely charged ion, this layer is called diffused layer. Why it's called diffuse? Because ions can go out and can come inside again. But this can't happen with the first layer, which is of the preferentially adsorbed ions. So this is how we have a double layer system around colloidal particles. These two double layers of oppositely charged ions are called Hallmund's double layer. Hallmund's double layer. And since these two double layers are having oppositely charged, they develop potential difference between them, and that potential difference is called zeta potential or electrokinetic potential. So the Hallmund's double layer always have a potential difference that's called zeta potential or electrokinetic potential. And this is being used in a number of ways to understand the colloidals. Electrophoresis, very unique and exclusive property to colloidal particles. Now we know that the colloidal particles are having charges of particular type on the surface, and due to this what we find is when we put them under the influence of electric field, they move towards one of the electrodes. So the movement of colloidal particles to any one of the electrodes under the influence of an electric field is called electrophoresis. So like this, if we have taken this U tube which is actually subjected to positive negative events, what we find is if you put a colloidal in this, they will move. Like if we have taken arsenic sulfide sol, we know it's a negatively charged sol. What will happen is its all particle will tend to move towards what? Positive plate. There, this movement towards positive plate is called, or this movement of colloidal towards any of the electrodes is called electrophoresis. Now, if suppose a sieve is placed here which blocks the movement of these colloidal particles to the electrode, what will happen is they will all aggregate here. Now, what will happen is the solvent, the medium is having high concentration on the above side of the sieve, whereas it has a very low concentration downward. So what will happen is the solvent starts moving from there to downward side, which is basically is osmosis. The movement of the solvent molecule from their region of higher concentration towards lower concentration is called osmosis. So this osmosis takes place, and this osmosis is taking place under the influence of the electric field, so it's called electroosmosis. So we can also have a phenomenon associated with this which is called electroosmosis. The last and the most specific and exclusive property of the colloidals is called coagulation or precipitation. The process of converting colloidal to suspension is called coagulation or precipitation. Usually we use this precipitation when a true solution particle is converted to suspension. But yes, it can be used here also. So more exclusive term is coagulation, where a colloidal range particle, colloidals are converted into a suspension. So we are able to see them. They forms a precipitate, they settles down. Now this process of coagulation is basically happening and it leads to what? Whenever we find a colloidal system is unstable, a colloidal is unstable, it coagulates. It changes to precipitates. Now coagulation of a colloidal can be done by various methods. The few of the methods of doing coagulation is discussed here. The first is by electrophoresis. Now we know electrophoresis, the movement of the colloidal particles to any one of the electrodes under the influence of the electric field. What happens to the colloidal particles when they reaches the electrodes? Their charge gets neutralized, and once their charges gets neutralized, they aggregates together to form a suspension range particles. They forms precipitates. So the end result of electrophoresis is coagulation. Second method, by dialysis of course, persistent. Now, if we allow the dialysis to take place for a very long time, what happens is all the ions, even the adsorbed, preferentially adsorbed ions, they also diffuses out. And as a result, these colloidal particles aggregates together to form what? Suspension or precipitates. So, persistent dialysis also leads to what? Coagulation. It can be by boiling also. See, if we are boiling a colloidal solution, what happens is, due to the high kinetic energy which these ions adsorbed and attains, they get desorbed. Desorption takes place. As a result, what happens is they aggregates together to form suspensions or precipitates. So it can be done by boiling. It can be done by adding oppositely charged soles. Yes, if you are having suppose a positive sole and you add a negative sole to this, they both will aggregate together to form a suspension or precipitates. Like if we have arsenic sulfide sole, which is a negative sole, and to this if we have added a positive sole, ferric hydroxide sole, they both will aggregate together to form what? Precipitates. And then we have one more method which leads to the formation of delta, that's called by adding electrolytes which are called coagulating agents. Like we know, the rivers are bringing along with them all the minerals in the form of colloidal. Now, the moment they reaches the sea, they meet the sea water, the salts present in the sea water acts as a coagulating agent. They neutralizes the charge which are there on those colloidal particles, and as a result, those colloidal particles, they aggregates to form a suspension or precipitate and settles down. So slowly and slowly, whatever the minerals the rivers are bringing along with them, those settles down on the river beds, the place where they meet the sea. And due to this, what happens is a very fertile land develops, which is called delta. The same is basically used here. You can add certain electrolytes in order to what? Neutralize the charges which are there on the colloidal particles, and so that they can aggregate to form precipitates. And those chemicals added which are called coagulating agents. Like we know, suppose we have a ferric hydroxide sole, which we know is a positively charged sole. Now we can add certain chemicals, like we can add sodium chloride, we can add potassium sulfate, we can add ammonium phosphate. So what we find is there is a rule for this called Hardy-Schulze rule, which states that the coagulating power of an ion is directly proportional to the charge present on it. And the coagulating ion must have an opposite charge, of course, that's what's required. So if for this positive sole, we can get chloride ion from here, we will be getting, like, let me indicate, like chloride ion from here, sulfate ion from here, and phosphate ion from here. So all these negative ions will be one which will be responsible for the coagulation of this positive sole. And out of these, since the charge, maximum negative charge is in the case of phosphate, so this ammonium phosphate will be having the maximum coagulating power for this ferric hydroxide positive sole. So Hardy-Schulze rule plays a very important role in deciding that which particular salt will be having a higher coagulating power for a particular sole or a colloidal solution, which actually is that the ion responsible for that should be the oppositely charged ion. It should have a maximum charge. So this is how we can cause, basically can lead to what? Coagulation or precipitation of colloidals. Protection of colloids. See, we know lyophilic soles or lyophilic colloids are already very stable. So they don't need any kind of a special protection in order to prevent them from getting coagulated. But yes, of course, the lyophobic colloids are unstable. We know they easily gets coagulated. So they needs to be protected from this coagulation. How? By adding lyophilic colloids. That's the best way. If we add a lyophilic colloid to a lyophobic colloid, those lyophilic colloids surround these lyophobic colloidal particles and performs a protective layer around them. And this is how, and since they get maximum hydrated or solvated, they will not be letting these lyophobic colloidal to come closer to each other. And this is how we can protect lyophobic colloidals. Such type of lyophilic colloids which are added to protect lyophobic colloids are called protective colloid. They are called protective colloids or protective soles.